Welcome to this Chapter 8 Sampling Distribution Statistics lecture video. We are going to be getting into the sampling distributions, and I refer to this as the average of the averages, right? Let's dive in. There are only two sections in Chapter 8, 8.1 and 8.2. And in 8.1, we're going to be talking about the distribution of the sample mean. There's two objectives. We're going to describe the distribution of the sample mean from a normal population and describe the distribution of the sample mean from a non-normal distribution, non-normal population. All right. So in statistics such as X bar, which represents the mean, they're basically random variables since their value varies from sample to sample. And keep in mind, there has been, randomization. As we collect the mean, we try to do away with bias. And so for that reason, the means will change from population to population as we collect samples. Like if we were to say the population of all Everett students, and let's say we decided to pull their 20 random students, and we decided to calculate the averages of their math class grades. 20 random students, average of their math class grades. Well, that one sample of 20 students will be one number, and if we get another sample of another 20, it will be more than likely different from the first sample. And so the distribution of those differences is kind of the thing that's in question right now. So we're going to focus on the shape as it's been plotted or jotted out, the center of the distributions, and the spread of the statistics. Alright, so the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. The sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the random variable x bar computed from a sample of size n from a population with mean mu and standard deviation segment. So the idea behind obtaining the sampling distribution of the sample means is as follows. 1. You obtain a simple random sample of size n, compute the sample mean, assuming that we are sampling from a finite population, repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. Which, if you think about it, would be an awful lot. I mean, if we have a population of, say, 1,000 of something, and we decided to collect samples of size 20, the amount of random samples that we'll get that are distinct samples would be astronomical. It would be a large amount, an extremely large amount, because we're talking about the permutations of all of the different numbers. Once a particular sample is obtained, it cannot be obtained a second time. So that's what we mean by that. So all the samples would be different. Describe the distribution of the sample mean from a normal population. So here is the question. It says an intelligence quotient, or IQ, is the measurement of intelligence derived from the standardized test. So there's one test called um, the Stanford-Binet IQ test. Scores on this test are approximately normal with a mean score of 100 and a standard deviation of 15. What is the sampling distribution of the sample mean for a sample of size n equals 9? Well, what we're going to see in the next slide, it shows this SRS, random samples from the Minitab. Row 1 contains the first sample where IQ scores of the 9 individuals are, 90, 74, 95, 88, 91, so on and so forth. The mean of these 9 IQ scores is 90.9. Row 2 represents a second sample with the 9 different IQ scores. Row 3 represents a third sample, so on and so forth. So let's look at this. There will be a lot of samples of size n. And if we compute the mean of each one, some of them will be really close, some of them will be very different from each other, but some may even be the same. Maybe we can spot somewhere it was exactly the same. That could happen. It doesn't seem so in this list, but again, those are the kind of things. So a 96.1 and a 96.2 are very, very close. Maybe if we were to look at more, we would see that maybe there are some that are very, very close. But it makes sense that they're different because we're dealing with different samples. So what do we have? If we chart out the means of all the samples, all right, it's going to show that the distribution of the population, and in figure B, it shows the distribution of the sample means. So we have the regular IQ scores from the population, and now we have the sampling distribution for sample size n of the average of all of the IQs. Notice that they are both normal, and there's one other glaring case that is going to become obvious, that the mean of the population is equal to the mean of the sampling distribution. That's key. The sampling distribution of sample sizes of, say, some n, some number n, that mean of that distribution, of that sampling distribution, is the same mean of the population. So all of those means that we were calculating in those averages, they were approaching the true mean of the population. In addition, we notice that the center of the distribution of the sample means is the same as the center of the distribution of the population, but the spread of the distribution of the sample means is smaller than the spread of the distribution of the population. In fact, the mean of the 1,000 sample means is 100.02, which is close to the population mean of 100. The standard deviation of the sample means is 5.01, which is less than the population standard deviation of 15. And so what they're saying is yes, although they will have the same mean, the standard deviation will not be the same. The standard deviation for the sampling distribution is smaller. So the range of values, it's more of a tight knit, but it is a normal distribution. So here are the conclusions that we can draw, that the shape of the distribution of the sampling means is approximately normal. The center, the mean of the distribution of the sample means equals the mean of the population, and the spread, the standard deviation of the sample mean is less than the standard deviation of the population. And if we were to repeat the same activity but with the bigger sample size of 25, we're going to get, again, the same normal distribution. The mean approaches the population mean, and the standard deviation is much smaller than the other one. So the figure on the previous slide shows that the histogram of the sample means, which histogram is good for pointing out we can see the distribution of the data with a histogram, and that's why we employ the histogram. It also can help us with the center. We can identify the center, we can identify the shape, and all of these things. The sample means appear to be approximately normal to the center of 100. The histogram in the figure though shows less dispersion than the histogram in figure B. This implies that the distribution of the means with n equals 25 has less variability than the distribution of means with n equals 9. In fact, the mean of the 1000 sample means is 100.05, and the standard deviation is 3.08. So the question becomes, what role does n, the sample size of our sampling distribution, play in the standard deviation of the distribution of the sample means? And what we are going to realize is that as the size of the sample increases, the standard deviation of the distribution of the sample means decreases. And here it is. It's actually the little sigma sub mean is the sampling distribution of means deviation. So it turns out it is the population deviation divided by the square root of n. So suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. The sampling distribution of mean has the mean equal to mu, but the standard deviation of the sampling means will be equal to the deviation of the population divided by the square root of n. The standard deviation of the sampling distribution of means, we call it little sigma sub mean, is called the standard error of the mean. The shape of the sampling distribution of the means, if x is normal. So if a random variable x is approximately normally distributed, the sampling distribution of the sample means x bar is approximately normally distributed. And here we have, let's get back there. Here we have the IQ scores of individuals are modeled by a normal random variable with mean mu 100 and a standard deviation sigma equals 15. The sampling distribution of the sample means the mean IQ of the simple random sample of size n is approximately normal, with the mean being a 100 and the standard deviation of 15 divided by the square root of 3. This 15 divided by the square root of 9, which is 3, which equals 15 divided by 3, which is 5. So here the IQ of x of humans is approximately normal with the mean 100, standard deviation 15. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. That is, compute the probability of a sample of size 10 being greater than 110. Well, in order for us to compute whether or not a sample of size 10 is greater than 110, we need the sampling distribution of all size 10 samples. And once we have that, we'll know that it is actually going to be normally distributed. The mean will be the same mean as the population mean. The sigma, the deviation of our sampling distribution, will be 15 divided by the square root of 10. We also need to verify that the sample is a random sample and the sample size is definitely less than 5% of the population. So we can now answer this question. We want to know what's the probability of getting a sample that has greater than 110. Well, if we're using the table, we'll have to convert these values into their t-scores, into the z-scores, and then compute the table. But what we're going to do is actually use technology here. All right. So we're going to use normal CDF under second distribute, number 2, and we're going to put in the lower bound, it's 110, the upper bound, some very large number. I'm going to put in 1 times 10 to the 9th power. That is a billion. That's overkill, but we just have to put in some large number. All right, 1,000 would have worked. Now we're going to put in the mean, which is 100, and we have to put in the deviation. Well, the deviation of this sampling distribution is not 15. It's 15 divided by the square root of 10 is what it is. All right, and then you close parentheses. Now, it seems like I didn't need a parentheses around that 10. Fine. Hit enter, and we got 0.0175. That is 1.75%. And that's exactly what they got. So how about we describe the distribution of the sample of means from a non-normal population? Here we have populations, it's non-normal. Here we're getting that the sampling distribution is skewed right. The sampling distribution's mean is equal to the population mean. Same as before, we're going to carry it out the exact same way. So as we increase the sample size, the sampling distribution will get normal, even though the data comes from a non-normal population. So here are the two things we need to understand. The mean of the sampling distribution of the sample mean is equal to the mean of the underlying population, and the standard deviation of the sampling distribution of the sample means is sigma divided by the square root of n, regardless of the size of the sample. And then 2, the shape of the distribution of the sample means becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. Let's take a look now at the central limit theorem. And basically the central limit theorem, it guarantees, it just says that Regardless of the shape of the underlying population, the sampling distributions of mean becomes approximately normal as the sample size n increases. Now the question is, well, how large does the sample size need to be before we can say that the sampling distribution of the means is approximately normal? The answer depends on the shape of the distribution of the underlying population. Distributions that are highly skewed will require a larger sample size for the distribution of x to become approximately normal. So we saw this happen as we were taking samples of size 4, samples of size 10, and samples of size 25. We saw different things happen there. And here's what we saw. Here's the original population. There's the sampling distribution of means of size 4, so on and so forth. And the bigger the sampling got, the more normal it went. And so here it's as if the distribution of the population is unknown or not normal, then the distribution of the sample means is approximately normal provided that the sample size is greater than or equal to 30. So that's kind of the rule. The sample size has to be greater than 30, and then we can basically assume that that it will be normal, and we can therefore use our guide. So here's a question, and it says that the mean weight gained during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determined that their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? It's a good question. I think one thing that's unusual is that the sample was not random. All right. Now, okay, the obstetrician says that it was a random sample, but there appears to be a little bit of bias, unless the population is of all low-income patients and all of the samples are from that. This could be true too. So, but since it says random, okay, we will carry on. Now the question is here, it says, does this result suggest anything unusual? Well, if we do our calculations and get something less than 5%, then that would be considered unusual. The sample is a random sample. It seems reasonable here that at least 700 low-income pregnant women in the population. So the sample size is less than 5% of the population. And this is what we would get, basically. The probability is represented by the area under the normal curve to the right. It's always good to make this type of diagram. The mean is 30. That's the average amount of weight. And then we want to figure out, what is this proportion? How many of those samples will be above 36.2? And so we know the mean. We're going to convert these values to the test statistics and then use the table to get our answers. But if we have technology, we can just use technology here. We'll get 0.0023, and that is less than 1%. I mean, that is extremely tiny. So the interpretation of this, if the population from which this sample is drawn has a mean weight of 30 pounds, the probability of a random sample of 35 women has a sample mean weight gain of 36.2 pounds or more is approximately 0.002. This means that about 2 samples in 1,000 will result in a sample mean of 36.2 pounds or higher. if the population mean is 30 pounds. Furthermore, we can conclude that the mean weight gain for low-income patients is 30 pounds, and we happen to select women who, on average, gain more weight. The mean weight gain for low-income patients is more than 30 pounds. We are inclined to accept the second explanation over the first, since our sample was obtained randomly. Therefore, the obstetrician should be concerned. Perhaps she should look at the diets and/or lifestyles of low-income patients while they are pregnant. Okay, there could be some lurking variables that can explain why it is so unusual. So here, this is the result. Okay, as you can see, regardless of the shape, whether it's normal or not normal, we get that the center, which is the mean of the sampling distribution, is equal to the population mean, and the sampling distribution's deviation is equal to the population deviation divided by the square root of the sample size. Also compute probabilities of a sample proportion. So here we go. Let's get into it. So suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion, denoted as p hat, is given by x, the number of people who have certain characteristic, divided by the total number of people in the sample. So x is the number, and p hat represents the sample statistic there. It estimates the population proportion p. Now p is the real proportion for the population, and p hat is the sample proportion. P hat is an estimation of p. We may not ever know p. That's why we deal with the sample, because samples help us understand the true population. So here's our problem. It says, the Harris poll conducted a survey of 1,200 adult Americans who vacationed during the summer and asked whether the individuals plan to work while on summer vacation. Of those surveyed, 552 indicated that they plan to work while on vacation. Find the sample proportion of individuals surveyed who plan to work while on summer vacation. Substituting x equals 552 and n equals 1,200 into p hat equals x over n, we find that p hat is equal to 552 over 1,200 equals 0.46. So Harris estimates that 0.46, or 46% of adult Americans who vacation during the summer plan to work while on vacation. Based on a study, here's another example, okay? Based on a study conducted by the Gallup organization, 76% of Americans believe that the state of moral values in the U.S. is getting worse. Describe the sampling distribution of the sample proportions for samples of size n equals 10, n equals 25, and n equals 60. So here we have the figure shows partial output from StatCrunch. The row 1 contains the first sample, where the result of the surveys are 1, success, 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 and O for failure, failure. The mean number of successes, that is the sample proportion for the first sample of n equals 10 adult Americans, is 0.7. Okay. Figure A shows the histogram of the 2000 sample proportions from column p hat. Notice that the shape of the distribution is skewed left. The mean of the 2000 sample proportions is 0.76 and the standard deviation is 0.136. Notice that the mean of the sample proportion equals the population proportion. Alright, here for bigger size, for sample size of n equals 25. Notice that the histogram is slightly skewed left still. The mean of the 2000 samples proportion of the sample means is 0.76 and the standard deviation is 0.08. And finally, notice that the histogram is actually approximately normal for the sample size of n equals 60. The mean of the 2000 sample proportions is 0.76 and the standard deviation is 0.054. So here are some things that we need to observe. The shape, the center, and again, the shape, as the size of the sample increases, the shape of the distribution of the sample proportion becomes approximately normal. And then also the center, the mean of the distribution of the sample proportions equals the population proportion. Spread. All right, well, the deviation there. Okay, so the standard deviation of the distribution of the sample proportions decreases as the sample size increases. And this is indicative of what we saw of the sampling distributions of means. So the sampling distributions of p hat. So for a simple random sample of size n with a population proportion p, the shape of the sampling distribution of p hat is approximately normal, provided n times p times 1 minus p is greater than or equal to 10, and the mean of the sampling distribution of p hats is mu p hat equals p. Now, here we go, the other part, and this is the important part. The standard deviation of the sampling distribution of p hat is sigma sub p hat, which is equal to the square root of p times q, when q is, again, the complement of p, 1 minus p, divided by the square root of the sample size. We're dividing by n, and then we're taking the square root of all of that. So now we have a formula. All right, so here's a question. It says, suppose that the proportion of Americans who believe that the state of moral values in the U.S. is getting worse is 0.76. Suppose we obtain a simple random sample of n equals 60 Americans and determine which believe that the state of the moral values in the U.S. is getting worse. Describe the sampling distribution of the sample proportion for Americans with this belief. Well, first of all, if we do 60 times p times q, we do get a number greater than 10. This is good. This means that the shape of the sampling distribution of size 60 will be normally distributed. And therefore, we know then that the mean will be 0.76, and this deviation of that proportion sampling distribution will be 0.055. Objective 2. Compute probabilities of a sample proportion. According to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 Americans, what is the probability at most 12% have hearing trouble? The data was obtained by a random sample. There are over 300 million people in the U.S., so the sample size of n equals 120 is definitely less than 5% of the population size. We are told that p equals 0.15 because n times p times 1 minus p is equal to 120 times 0.15 times 1 minus 0.15 equals 15.3 is greater than 10. The shape of the distribution of the sample proportions is approximately normal. Now, we now know that the mean is 0.15 and the deviation is this. And we want to know that the probability that a random sample of 120 Americans will result in a sample proportion at most 0.12. So that is, we want to know that the probability of p hat less than 0.12 matches this. Well, what we need to do is either use technology at this point. Again, this is our normal distribution. It's not the standard normal distribution, but it is a normal distribution. Remember, the standard normal distribution, it has the mean of 0 and a deviation of 1. This has the mean of the purport of the population, but the standard deviation is this number. Let's continue. So now we're going to convert our 0.12 and 0.15 into the z-score. And now we get 0.1788, and we should also be able to get that using technology. Let's get this same value using technology here. So we simply have to do normal CDF. The lower bound, well, let's go back for a second. Yeah. The lower bound, we're going to have to just put in a negative number. So I'm going to put in negative 1 e to the 9, negative a billion, comma, 0.12 is my upper bound. Our mean is 0.15. And the deviation well, we never truly figured out what that deviation was. We actually have to use parentheses there. It's going to be the square root of 0.15 times 0.85 divided by 120, which is the sample size there. And then close that off. Hit enter, and we're getting 0.1786. If we round it off, we get 0.1787, and that's what we got there, 0.1788. And so we could use technology to figure this out as well. And now we would make our interpretation. And yeah, we finally can conclude. We can answer the question. This is another question. So we're giving that 120 Americans have trouble listening using headphones. So the sample proportion is 0.217. And we want to know what is the probability of more people, a sample of 120 will exceed 0.217. And again, a normal distribution, the mean is 0.15, the standard deviation is what it is, and we simply get 0.0197. That is almost 2%. So out of 100, 2 people will, 2 samples, I should say, out of the 100 samples, 2 samples will have a sample proportion of means greater than 0.217. Okay? And finally, what can we conclude? This is what we can conclude. Okay, so the interpretation, you could make one of the 2 different conclusions, that the population proportion of Americans with hearing trouble who regularly listen to music using headphones is 0.15, and we just happen to randomly select a high proportion that have hearing trouble. Or we could say the population proportion of Americans with hearing trouble who regularly listen to music using headphones is more than 0.15. Now, let's take a peek at some of our practice problems here, and we're going to let's go inside 8.1, and you must do 8. 8 comes before 10. The naming convention, because there's a 1 and a 0, it's sorting section 10.1 before it sorts 8.1, and it's there basically needs to be a better naming convention. Probably could have put in 010 or 8008 and something like that, to kind of where when it's putting it in alphabetical order, it thinks that 10.1 comes before 8.1, but truly 8.1 comes before 10. 10.1 is from chapter 10, and we're just not there yet. Let's take a look at 8.1. This is with the sampling distribution of means. Does the population need to be normally distributed? Here, let's see if we can try to make this a little bigger. It seems kind of small, hard to see. This is good. All right, this is an application of the central limit theorem, which basically says regardless of the underlying population, the sampling distributions of means will approximately be normal as the sample size increases. Well, mu is still going to be equal to 82, because that is what we learned from the sample population there. Yeah, but this one is actually going to be 22 divided by the square root of 33. Now, they wanted me to enter in 3 decimal places. If I enter in the exact value and hit check, will they give it to me? No. You actually have to plug it into your technology and do it that way. So I'm gonna do that. Okay, so let's do 22 divided by the square root of 33. Enter. 3.829, so 3.830. Well, here's the population. It's 500. What would the value of the sample mean be? 500. What would the value of this be? Well, we first have to know the sample size, and then, well, actually, we probably could figure it out without the sample size. We could just say 30, because the difference. Wait, hold on. Let's see. Um, what is the value? So it would be just 30. One deviation appeared to be 30 more on that one. Now, if the sample size, I would say 10. Well, n equals 9 is actually n equals 9 is not a very big sampling distribution. Um, so it might be skewed right a little bit. Let's see here. This is a tough question. Yeah, it's going to be hard to determine, because we don't have a big enough sample size, and it's wrong for us to just say that it'll be skewed one way or another. Let's go with this. Oh, okay. The shape will be. Oh, that was a little misleading. That was kind of a tricky question there, but okay. I think it's probably it's the best choice. It's the best choice there for that. If the sample size is n equals 9, what is true about the shape of the population? Oh, oh yeah, shape of the population, sure, but I thought they were talking about the shape of the sampling distribution of sample sizes of 9. But the question was, what is likely true about the shape of the population? So we didn't read it right. We thought if the sample size is okay, yeah, the population is normal. That's the assumption in this section. Yeah. All right. Yeah, these are just regular problems. Remember, you're going to be using the sampling distribution of size 81. The square root of 81 is 9. So again, you're going to be doing 71, and then the square root of 9 is the sampling mean would be 71, and the sampling deviation will be 27 over 3, which is 9. The square root of 81, 27 divided by the square root of 81, which is 27 over 9, which equals 3. So the sampling distribution will actually be 3, and the mean of the sampling distribution will be 71. And we're dealing with a nice big size, so we'll say it is approximately normal. And what would this be? It would be 71 and 3. And then finally, what is, now you would draw this out, a normal distribution, and we're going to go from 75.95 and above. So our lower bound will be 75.95. Our upper bound will be infinity, some large number. Our mean would be 71, and our deviation would be 3, and you will get your answer there. Okay, let's look on, um, let's take a look at 8.2, some questions from 8.2 now. 15 questions, not bad. The blank, the sample proportion is denoted as p hat is given by the formula x over n, where x is the number of individuals. There we go. Let's go. Let's go. True or false? The population proportion and the sample proportion always have the same value. I'm going to say true. Yeah. Why not? Well, no, they don't. They don't always have the same value, but they approximate the same value. What kind of tricky question is this? Okay, no, of course they don't always have the same value, but theoretically, we use that was oh my God, that was bad. Okay. Select the correct choice that complete the sentence here. All right. The mean of p hat should be equal to this, the mean of the population. Um, all right. So this was a little misleading. I have to admit, this looks like the sampling distribution of p hats, where the mean of the sampling distribution. Um, So it should have been p hat is what it does. It approximates that. Yeah, that was, I don't know why I missed that one. Let's keep going. Describe the sampling distribution of p hats. Assume the size of the population is 30,000. Um, first of all, does this work? Like if we do n times p times q, do we get a number bigger than 10? And we do. Um, Determine the mean of the sampling distribution of p hat. So it's just going to be the sample proportion there. So It would be, I believe, just 0.3. Let's put in 0.3, which is what we were given. Oh, wait, hold on. We have, so wait a minute. We have the population as 0.3, but the sample is 600. So if we do 0.3 times 600, let's see here. We get 180. And if we do determine the mean of the sampling distributions of p hat, I'm gonna go with that. Let's see. Yeah, that, I don't know why that was so tricky. Okay, so this is actually, there's a formula for this. It is the square root of p point, 0.3 times the mean, 0.3 times q, which is 1 minus, which is 0.7. And then we're going to divide by 600. So we got 0.3 times 0.3 times 0.7 divided by 600, and we take the square root of the last answer. Alright, so that 1.05 e to the negative 4 is scientific notation. The number was so small, but now after we take the square root, we're actually getting 0.01024. They want 3 places, so 0.010. Just 0.01. Point 20. Hold on. I think we multiplied by too many threes. It's 0.3 times 0.7 divided by 600. And now take the square root of that last answer here. 0.019. So here we have the problem. It says, how likely are the results of your sample if the population proportion of voters in the town in favor of the referendum is 0.548? Yeah, so that's just a matter of plugging in the values. The probability that more than 106 people voted for the referendum is blank. So it shouldn't be too difficult to figure out. Again, we know that since the population proportion is 0.48, the sampling proportion will have that same value. Q will be 1 minus this value, and we're going to divide by n, which is 200. That size there. All right, hopefully this is helpful, and let me know if you have any additional questions or comments, and we'll be back in touch.